So, now in this lecture we shall be starting from where we left in the last lecture, and we shall be looking at what kind of modifications we need in the micro operations and also in the data path if we want to pipeline our MIPS 32 means instruction set architecture implementation. Now, means one thing is happening naturally, because earlier we talked about 5 different stages of execution or steps of execution. So, for the pipeline implementation also we shall be retaining that same definition for the pipeline stages. The same 5 steps we will be converting into pipeline stages. Okay. So, this is the title of our talk. So, first we look at what are the basic requirements for pipelining the data path that we have seen in the last lecture. So, what are the things to be done? Well, in a pipeline, what we have seen earlier through some examples, the main motivation for having a pipeline is that our input data is arriving continuously once every cycle. So, we should be able to feed one new data every cycle. Now, in this case we are talking about instructions. Our instructions is like our data. In every cycle a new instruction is coming, a new instruction is fetched. Okay? This is how the pipeline will be executed, and this is called this is referred to as instruction pipeline, because this is a pipeline where instructions are executing and instructions are moving from one stage to the other, IF, ID, EX, MEM, WB. Okay? Fine. So, the one requirement is that we should be able to start a new instruction every cycle, because otherwise this pipelining will not give you the desired advantage. And as I had said, the 5 steps that we had mentioned, these 5 steps, we will make them as 5 pipeline stages, IF, ID, X, MEM and WB. Now, of course, one thing is important, you see there is a global clock. With clock the data and the results are moving. So, every stage should be able to finish its execution within a clock cycle. Okay? So, that is another requirement. Each stage must finish its execution within a clock cycle. So, our overall pipeline will look something like this. These will be the 5 stages, and there will be pipeline latches separating the stages, just like we saw earlier. For isolation we need these latches, because when the first instruction has moved from IF to ID, its temporary data are stored in this latch. So, ID can very peacefully do the instruction decoding, because these data are stored in the latch, and meantime the second instruction can be fetched in IF. But if you do not have this latch, while IF is going on, this data will keep changing, and so the process of decoding might get disturbed. Just for isolation we need the latches. Okay. Now, in instruction pipeline, the advantage that you get is pictorially depicted like this. You see, in this direction we show the time, the clock cycles. Let us say our instruction number I is coming. Let us start with clock cycle number 1. So, it is fetched, decoded, executed, MEM and WB, it is finished. Now, in pipelining what we do, when the first instruction I moves from IF to ID, the next instruction in sequence it can start IF. So, in time step 2 the first instruction is in ID, then next instruction is in IF. In third step the first instruction has moved to EX, second in ID and third in IF. In this way you see, fourth step MEM, IX, ID, IF. Fifth clock cycle WB mem EXID. Now, say after this WB, the first instruction I will finish. So, it will finish here after 5 cycles, and after 6 cycles I plus 1 will finish because WB is finished here, and after 7 cycles I plus 2 is finished, and so on. So, here the idea is that you initially give some time for the pipe to fill up, and after it gets filled up you will be getting one instruction completed per clock cycle. This is the advantage that we gain in pipelining. You also saw the examples earlier. If there are 5 stages, you can in the ideal case expect 5 times speed up. But of course, in instruction pipeline there are other constraints, we will talk about it later, that limit the speed up. It may not be exactly 5, in fact much less than that, and I plus 3 here. And this is a picture you also saw earlier. For this case also we need a register bank that will be having 2 read ports and 1 write port. So, there will be 32 registers, that is why the source and destination registers are 5 bits each, and each register is 32 bits long. So, the register data are all 32 bits, right. Okay. Now, let us try to modify the micro operations for the pipelined MIPS 32 version. Now, the first step is that we need to follow some conventions for this, because the conventions that we are talking about it with respect to the naming conventions, and we will be consistent with naming. That means, whatever we show on the slides, the same convention we will be following when we show the Verilog codes. Okay. Now, the idea is as follows. You see, you have these 5 stages: instruction fetch, instruction decode, execution, mem, and write back WB. Now, what I am saying is that you see there will be before and after also, but the most important latches are those are between the stages. Okay. So, for our interest we need these 4 interstage latches. We give some names to these latch stages. We call this stage as IF underscore ID. That means the latch stage that is sitting between IF and ID. This latch stage we call as ID underscore EX. We call this EX underscore mem, and we call this mem underscore WB. So, this is the convention we will be following. The latch stage we will be representing using this underscore notation, between which pair of stages this latch stages. Okay. Fine. So, this is the convention that I have just talked about: IFID, IDX, EX mem, and mem WB. And another thing, the temporary registers that we have talked about. Let us take an example. Now, in the IF stage, just look at the IF stage. In the IF stage, you recall there was a micro operation which said that instruction register was loaded with memory location whose address was in PC. So, the data must be stored in some register IR. So, where is IR? So, IR, will it be some separate register inside IF? It is actually no. Actually, just like in the example that you showed earlier, that all temporary registers will be part of the latch or the register stages. Let us say this one, this itself can be IR. So, and this register actually we will be referring to as IF underscore ID underscore IR. This is the kind of naming convention we will be following. And in case this register is also forwarded here, let us say maybe this IR will require later also. So, here also there will be an IR. and this IR will be calling as ID underscore EX underscore IR, and this same IR we will also be forwarding here. So, here we will be calling it, there will be an IR register here, we will be calling it EX mem IR, and again this will also be forwarded here, this will be calling mem WB. Now, the reason I have taken the example of IR is there is a reason for good reason for this. You see, this IR is just one example. There will be many other registers which will also be just handled the same way. For example, in the instruction decode, when you prefetch the register bank, there will be one register called A, another register called B. They will be similarly named IF, this will be IDEX, this will be IDEXA and IDEXB. Now, the reason that we have to forward it like this, you see, instruction register will contain the entire instruction format, all the source register, destination register. For some of the instructions, you need to take the decision only at the end, let us say write back. For some instructions you are writing into register RD, for some other instructions you are writing into RT. So, both the values of RT and RT should be available to you, that is present in this instruction IR, and you need to forward it because when instruction I has reached WB, let us say here you have instruction number I, your next instruction is here, next instruction is here, and I plus 3 is here, and so on. So, whatever IR is stored here, that is the IR of instruction I, and whatever IR is stored here, that is the IR of instruction I plus 1. This is the IR of instruction I plus 2, and this will be the IR of instruction I plus 3. Okay? So, this explains why we need to forward the same register across stages so many number of times, because there are so many instructions moving and each of them will be needing their own IR. Okay? Their instructions are different, so their IR will also be different, that is why. Okay. So, now let us straight away look at the micro operations for the different stages, well, assuming that we are having a pipeline implementation. First, the instruction fetch. You see, here whatever we are showing, we shall be directly translating them into Verilog code later. We are fetching the next instruction mempc. Earlier we mentioned that we are storing it in IR, but now we are saying it will be IF underscore ID underscore IR. This IR will be as part of the IFID latch. Then we check whether the opcode is a branch and the branch condition is true. You see, a branch instruction is fetched, decoded, but the branch condition will be known only when it has reached the EX stage. Just you see this diagram once more. See an instruction, a branch instruction. So, once it reaches the EX stage, only then you know that is a branch instruction, and the values of the cond and the next instruction address will be stored in this buffer. So, if you decide that there is a branch, so the next instruction has to be fetched from that address. So, there has to be some kind of a feedback from this back to here. Next instruction fetch will depend on the outcome of these conditions of the branch, right. That is reflected by this micro operation you see. Here it is saying if the instruction register in the EX mem, you see EX mem is this one, EX mem, opcode was a branch, and the corresponding condition, branch condition was true, then only branch will take place, you see. So, if exmem opcode is branch and exmem's branch condition was true, then whatever branch target address you have calculated in ALU out, exmem ALU out, that will be assigned both to IFID NPC and also to PC. Else, if this branch it is not a branch or the branch condition is not true, then simply PC plus 1 will be assigned to these two. Okay? Fine. So, in terms of hardware, the instruction fetch stage will look like this. This will be your IFID stage, instruction memory, IR will be part of this NPC will also be part of this. Okay? And as I said, from mem out stage, EX mem stage, these two signals are coming. Right? So, you are just calculating the NPC accordingly, and after calculating NPC, that same value also goes to PC. You see previous one, PC and NPC both are getting the same values. Well, else PC plus 1, if the branch condition is, if cond is not true, then the lower input will be selected from the multiplexer, that is PC plus 1, that PC plus 1 will go back to PC plus 1. Now, see, one thing is true here, see, for a non-pipeline implementation, we were storing the next address in NPC. Much later, NPC was copied to PC, but in a pipeline we cannot afford to do that. Why? In every cycle we are fetching a new instruction. So, we will have to continuously update the PC in every cycle. That is why we made this change here. In every cycle we are updating also the PC, right. So, the PC is getting updated directly here. Fine. Now, let us move to the ID. Well, ID is very similar, only the variable naming convention has changed. See, reg, earlier we said reg RS, but now we are saying IFID IR RS of that, IFID IR RT. The two registers are prefetched, they will be stored in IDEXA and IDEXB. Similarly, NPC is just copied, IR is just copied as I said, and IMM is sign extended. So, IFID IR, these bits will be sign extended to IDEX IMM. So, in terms of the hardware, it will look like this. Register bank, so NPC will be copied, this IR will be copied, that IMM part of the IR will be sign extended to get IMM, RS and RT they will be prefetch, register bank will go to A and B, and from memWB ALU out or LMD the data will be coming for writing into register bank, and from memWB IR the target will be coming. This will be either RD or RT. So, here although I have written RD, but this can be RT also depending on the type of instruction. Okay, this is how it will be in this stage. Similarly, for the EX stage, depending on the instruction type, micro operations will vary. For register ALU operation, first this IR has to be copied across every stage. IR is simply copied, and A, the function whatever add, subtract, multiply, B will stored in ALU out. But these variables are all prefixed by the pipeline latch number. Similarly, register memory ALU, IR is copied, and here instead of B it is IMM. For load store, IR is copied, this A is added to immediate data to compute the effective address, and B is also copied, because for store instruction this B will be stored. So, B also you need to copy forward, so that in the mem stage you can execute the store instruction. And for branch, you add NPC and IMM, because NPC was coming, and you check the condition A, equal to 0. That condition can be either true or false, that is stored in cont, exmem cont. You recall this exmem cont actually is being used here. You see earlier this exmem cont I showed here in the fetch instruction fetch stage, this is coming from there. Okay. So, the EX stage, the hardware will look as simple as this: ALU with some multiplexer, it can either come from NPC, or these are all part of this latch NPC A, B, IMM, IR. So, all these registers are here, and in the output here cond is there, ALU out is there, B is there, IR is there. Now, let us come to mem. For ALU operation again IR is forwarded and also ALU out is forwarded, nothing else to do in mem. Simply forward the data because you will be using them in the next stage. Load, IR is forwarded and you do a memory read. So, ALU out contains the address, you read it and store in LMD. For store, you see B was forwarded earlier, this B is getting written to memory, ALU out is the address, right. So, this will be your mem, ALU out is the address and B is for write and LMD is for read. And from this cond and this ALU out are going to the previous stage as we showed earlier. Okay. And IR is again forwarded and also ALU is forwarded to the next stage. Lastly, for WB, you see here both LMD and ALU out are used, that is why LMD is forwarded, LMD is there, ALU out is there and also IR is there because IR you require RD or RT. So, if it is a register ALU operation, then ALU out will be stored in RD, that register. For register memory, it will be stored in RT. For load, LMD will be stored in RT. Fine. So, here your WB is nothing but a multiplexer where you will be selecting either LMD or ALU out depending on the control signal, and it will be going to your means ID stage. So, it will this IR will contain which register number and this will contain what is the data. So, if you combine everything together whatever we have discussed so far, you see the picture looks like this. Just see the simplicity of the thing, the whole processor pipeline is fitting within a single slide. Okay, let me just make it bigger, this, yeah. You see this is your instruction fetch, decode, execute, memory, WB. Just let us proceed with one just example, let us say add R1, R2, R3. So, what happens in IF, PC contains the address of the instruction, it is fetched. So, the instruction is loaded in IR. Here the two operands are prefetched A and B, the two source operands. In for EX, this A is selected, B is selected, they are added, result will be stored in ALU out. For memory it does nothing, ALU out is simply forwarded, and for WB this ALU out will be written back into the register bank, and this IR will contain which register number. You see this is the simple data path that we have shown. Just one thing I wanted to clarify here, you see here I am not trying to teach you what is a processor, what is a pipeline processor, how to design a pipeline processor. Basically I am taking it as an illustrative example to tell you how we can model complex pipelines in Verilog. Okay. Now, well, because we have taken the example of an instruction pipeline, let me tell you a few things. Well, for a pipeline you may imagine that, well, if I have a k stage pipeline, I can have a speed up of k potentially when there are large number of data coming one after the other. But when you talk about instructions, there are a number of other problems that may come. There are situations which are called hazards. these hazards can happen in pipelines. First kind of hazard can be structural hazard. So, what is a structural hazard? Structural hazard say means two instructions which are already there in the pipeline, they are in two different stages, but they are trying to use the same hardware resource. If there is a single copy of the hardware resource, they cannot access it together. So, one of them will have to wait and the other can proceed. This is an example where you may have to insert a so called stall cycle in a pipeline, that means one clock cycle may get wasted. Like you see an example here, in this pipeline, in the IF you are fetching instructions from memory, and in mem for load and store instruction also you are accessing memory. Suppose if you had a single memory, then you could not do these two things together. That is why you see I have separated them out, instruction memory and data memory. I have separated out the two memory so that this kind of structural hazard can be removed. So, instruction will be stored in one memory, data will be stored in another memory, something like that we can assume. There are other more important kind of hazards, like there is something called data hazard. Data hazard can arise due to instruction dependency. Let us take some examples. Let us say I have an example, just add R0 to R3 followed by a instruction, let us say subtract, let us say R5, R1, R3. This is one example. Let us take another example, load R10, let us say 25, R3, add R12, R10, R6. Let us take this another example. So, you see one thing, here the first instruction is generating R1 which is being used in the second instruction. Here it is generating R10, it is used in the second instruction. So, you think like this, first instruction add, this was going through instruction fetch, instruction decode, then execute, mem, then write back. So, under normal circumstance this R1 will be written, result will be written only during WB, but for the next instruction you see sub instruction, here fetching will be done here and we will be trying to do instruction decode and register prefetching here, but because R1 is not yet ready, so here you will not be able to fetch the correct register value. So, you will have to wait, maybe possibly you can do your instruction decoding and prefetching here while this is being written. So, two cycles you may have to stall in between. Same is the case for here, you are loading an instruction into memory, this will be done only in the mem stage, and in the next case you are using that value R10. So, again R10 will be written in WB, again something similar will happen. Well, there are methods to reduce the impact of this kind of hazard, there is something called data forwarding and other things, but this is something you have to remember. Later on when you see some examples on the Verilog implementation, we will see that for sample programs we have to deliberately insert some dummy instructions in between such that the result is correct, otherwise this kind of hazard will take place and the next instruction will try to read some wrong value instead of the value which is being computed by the previous statement. Okay? And the third kind of situation is called control hazard. This arises because of branch instructions. Like you see, a branch instruction has entered the pipe. Now, you take the decision of the branch only after EX, right. So, when the branch instruction has entered the EX stage, already 2 other instructions are already in the pipe. So, when you decide that you have to branch, so those 2 instructions have to be discarded. So, these are some reasons why you cannot utilize the pipeline to the fullest possible extent and there can be some stall cycles. But again I am telling you, in this class, in this sequence of lectures, our objective is not to teach you computer architecture, but rather we want to teach you how to model this kind of pipelines in Verilog. So, all these things we are just assuming that these are required, that is why we are doing it. We are not going into the detail or we are not talking about any analysis on that. So, with this we come to the end of this lecture. From the next lecture onward, we will be actually looking at the Verilog implementation of this processor that we have discussed and talked about so far. Thank you.